Hello, everybody, and welcome back to another lesson. We're going to be doing the ideal gas law today, and this one has about 6-7 minutes of theory, and then we'll be doing a bunch of the math problems again. Super easy math. The theory is a little trickier. So what I'm going to do is I'm going to talk for a couple of minutes to give you an overview of the theory, and then I'm going to go to a video by Professor Dave, who does a beautiful job of summarizing it all, and then we'll get into the math. So we've looked at Boyle's law, Charles' law, the combined gas law, and today we do the ideal gas law. So the term ideal comes from the idea that an ideal gas is fictional, hypothetical. There are no ideal gases, but if they did exist, they would obey all the gas laws perfectly under all conditions. So that means Charles' law, Boyle's law, combined gas law would always work. The math would work for every situation. And in fact, it doesn't. There are no ideal gases, but some are closer than others. So why is that? What's going on with these ideal gases? Okay, so let's move on. To be an ideal gas, you would have to have no intermolecular forces. That's key idea number one. Now, that's not true. There are no gases that have that because everything has intermolecular forces, right? If you have electrons, you have London forces. If you have any polarity, you have dipole-dipole. Then you could also have hydrogen bonding. So, for example, a gas with just London forces might be argon. A gas that's polar could be, let's go, HBr. And then one with hydrogen bonding would be water. So all of these things have intermolecular forces in their gas phase, so they're not ideal. Okay, so if you had no intermolecular forces, if you were ideal, when you collided, you would bounce away from your neighboring molecule without any attraction. And we know that's not true. They do stick together and they do have some intermolecular attraction. So that's point number one. Okay. Point number two, which is not listed here, is they have no volume. And we know that's not true. Yes, the volume of the particles is really small compared to the volume of the gas, but there is still a tiny amount of volume. Okay, so here's my thinking question for you. Under what conditions are gases more likely to act ideal? In other words, if they collide, there's no or very little intermolecular attraction. When temperatures are high or low. So when temperatures are high, they're moving fast. And when temperatures are low, they're moving slow. So which of those conditions would create less intermolecular attraction? A fast collision or a slow? Hopefully you chose fast collisions for high speed. If you come in at high speed, you're more likely to bounce off of the other molecule without sticking around to have that intermolecular attraction. Okay, scenario number two. What about when pressure is high or low? Which of those is going to be more likely to create an ideal gas where there's very few intermolecular forces? So when it's high, they're close together, they're squeezed in, and when pressure is low, they're far apart. So which one of those is going to create a scenario where you are less likely to have intermolecular attractions? When you are closer together or farther apart? And hopefully you chose low pressure, far apart. So those are the two scenarios when gases behave ideal. At high temperatures and low pressures, the attraction between the particles is very small because the particles are moving fast and they're far apart, less chance of intermolecular forces coming into play. So this explains what an ideal gas would look like. Or condition, what ideal gas conditions would be. Okay, so now what I'm going to do is jump to Professor Dave. He's going to go through like a 3-minute review with you guys of ideal gases. Very, very well done. So take a look.
Professor Dave, let's talk about ideal gases.
He knows a lot about the science stuff. Professor Dave explains.
Let's recall our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate, so these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law, P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant, or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles'. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the gas, our dimension.
Okay, so that's where we stop with Professor Dave. As you can see, he's a lot better at this than I am. Polished pro. Okay, so now we're going to look at the ideal gas law, and we're going to jump into the math. So as he said, PV equals nRT. The textbook uses the formula. I don't. We're going to be solving by units instead, which I think you'll find easier. He was just alluding to R, the universal gas constant. You need to know that term. And this one is on your data sheet, so you don't have to remember the crazy units. You've probably never seen a number before that has 4 different variables in the unit. So 8.314 kilopascal liters on top, mole Kelvin on the bottom. And the ideal gas law, PV equals nRT, actually comes from Boyle's law, P1V1, and Charles' law, V1 over T1. And those equal constants. N, the number of moles, stays constant, and R is a constant. So this is where PV nRT comes from. You don't really need to know that, but in case you were curious, it didn't just get pulled out of thin air. Hey, there's a gas pun for you. Okay, so how do we use this to solve? Let's take a look. So first of all, you need to know the names, the symbols, and the units. So pressure, symbol P, unit, kilopascal, volume, V, units, liters, moles, symbol of N, units of mole, ideal gas constant, R, and it is kilopascal liter over mole Kelvin. And we usually keep the 8.314 in there. And then the last one is temperature T, and our unit is Kelvin. And Professor Dave reminded you how to convert degrees Celsius to Kelvin. Okay, so let's rock and roll. You've got your notes to follow along. We'll do some quick problems, and then you'll be good to go. Okay, first one. What chemical amount, so we're looking for N or moles, what chemical amount of gas is contained in 22.4 liters at STP? Now we could take our shortcut because we know that at STP it is 22.4 liters per mole. So that means in 22.4 liters we have 1 mole. We're going to solve this though using R, the ideal gas constant. So we know that at STP it's 0 degrees Celsius or 273 Kelvin. And there's our pressure. So how would you solve this problem using R? Okay, we're looking for moles. There's moles. So we're going to solve by units. So if we're looking for moles, we need to put that on top. So I'm going to flip R like this and have moles on top. So mole Kelvin over 8.314 kilopascal liter. Now to solve the question, we need to cancel out the units we don't want. So we need to cancel out Kelvin. So how do I cancel out Kelvin? I put Kelvin's on the top. I need to put it on the bottom. And here it is, 273 Kelvin. Okay, Kelvins cancel out. Now I need to cancel out kilopascals and liter. So they need to go on top. Kilopascal on the bottom. There's 101 kilopascal on the top. Okay, and I need to cancel out, switch colors again. Let's go back to black. Okay, so now I also need to cancel out the liters. And there it is, 22.4 liters. 22.4 liters. Liters on top, liters on the bottom. Okay, so I have canceled out all 3 of those units with these 3. And all I have left is moles, which is what I want. I'm solving for moles. And it's on top. So now it's just multiplying these numbers. 101 times 22.4 divided by those 2 on the bottom, multiply together in brackets. And when you plug those in, you should get 0.997 moles. And it's 3 sig digs. Everything in the question is 3 sig digs. The 0 degrees Celsius doesn't count because it gets converted to Kelvin, which has 3 sig digs. So that is how you use the ideal gas law or the ideal gas law constant R to solve these problems. And you'll notice that's really close to what we predicted with our shortcut. 1 mole is almost the same as 0.997 moles. Okay, let's try one more. I will try a few more. You'll discover these go pretty fast. So now we're going to solve for 1 mole of gas at SATP, but we're going to use R to do it, so we can't take the shortcut. So the shortcut would be volume of gas. Well, we know at SATP it's 24.8 liters. That's messy. 24.8 liters per 1 mole, and we have 1 mole. So let's see if R gives us that value. Okay, find the volume. V. Volume, we're looking for liters, and we have to use R, 8.314 kilopascal liters over mole Kelvin. All right, so liters is already on top, so that's where I'll leave it. 8.314 kilopascal liters on top, and my mole Kelvin on the bottom. Okay, so to solve this question, I need to cancel out everything except the liters. So kilopascals goes on the bottom. Pressure is 100 kPa on the bottom. Okay, I need moles and Kelvin on the top. So that's 1.00 moles. And Kelvin is plus 273 is 298 Kelvin. Okay, cancel out. Kelvins cancel. Moles cancel. Kilopascals cancel. And we are left with liters. Do the math and you get 24.8 liters. Okay, so the shortcut agrees with the long way of solving it using R. Now you're probably saying, well, why are you teaching us R? We have these shortcuts. That's true, but they only work for those two conditions, SATP and STP. The rest of the problems, you're not going to be given those conditions. So, for example, this time we have different conditions than STP and SATP, and we're solving for pressure. Okay, so pressure, symbol, units, kilopascal. So how do we do that? Well, we need R. And R is kilopascals is already on the top, so that's how I'm going to put it. 8.314 kilopascal liter over mole Kelvin. All right, there's our kilopascals. That's what we want. Let's get rid of the other three. Liters goes on the bottom to cancel out with this liters. I need moles and Kelvin on the top, 30 moles. Okay, those cancel out. And Kelvin, 40 degrees Celsius plus 273 is 313 Kelvin. And Kelvins cancel out. Okay, everything cancels out except kilopascals. Plug it all into your calculator and you get 1,561.36 kilopascals, and we're only allowed 2 sig digs, 1.6. There's our 2 sig digs, and we had to move the decimal 3 places, times 10 to the third kPa. Okay, I hope at this point you're thinking, hey, this isn't too bad. I can do this. It's actually pretty easy. Okay, we'll do another problem. Okay, we've got 2.25 moles of hydrogen in a 150 liter balloon at this pressure. What is the temperature? Okay, so the symbol, we're solving for temperature. We're looking for Kelvin. And we're going to use R. 8.4 kilopascal liter. Okay, I've got to flip it because I need Kelvin on top. So mole Kelvin over 8.314 kilopascal liter. Remember, the 8.314 always has to stay with the kilopascal liter. So Kelvin is on top. That's where I want it. Perfect. Whoops. That's times. I just need to get rid of those 3 variables. So moles goes on the bottom. 2.25 moles. Okay, moles is gone. Kilopascal liter on the top. 220 kilopascals gone. Switch colors and liters. 150 liters. Liters cancels out. Aren't these easy? It's all about the units. Okay, plug it into your calculator and you get 1,764.09 Kelvin. And looking through the question, 3 sig digs, so 1.76, and I moved it 3 decimal places. Whoops, temperature, not pressure. Kelvin. Okay, how's everybody feeling about that? Homework for you. I'd like you guys to try the ideal gas law worksheet in your study guide. Page 172, numbers 1 and 2. That's actually textbook, I believe. I'm going to verify that right now. No, it is in your study guide. Okay, page 172, numbers 1 to 2 in your study guide. And then, ironically, in your textbook, there are also some questions very close by on that page number. I'm just going to verify that one. Yes, 174, numbers 3 to 5. And you can work on those and have them ready to go. Tomorrow, what we're going to do is just one more addition to the ideal gas law. So today was called 1-step problems. Tomorrow is 2-step. Super easy. You're going to love it. Okay, have a good day, everybody.